So, now we will try to look at the second part of the proof, but let me review for you the weak form again. So, let us write it down. So, given f, g and h as before, we are supposed to find a u that belongs to the solution space S such that for all w's that belong to V, I must satisfy this condition that 0 to 1 w comma x u comma x dx, this is equal to 0 to 1 w f dx plus w times 0 h. This is the weak form. Now, a couple of interesting aspects of the weak form. The first one is that this has to be satisfied for all w's. Okay. So, when you say that my solution satisfies the weak form, that means I am free to pick any w I want and the weak form has to satisfy this statement. Okay. We have already defined what S and V are. Let me rewrite them for you. So, S is the set of all functions u such that u belongs to H1 and u1 is G. Similarly, V was the set of these functions w such that w also belongs to H1 and w1 is 0 at the homogeneous Dirichlet boundary condition. Okay. Now, please notice that in this weak form of the problem, out of the two boundary conditions, there is one which is satisfied explicitly. Okay. But the boundary condition, which was the Neumann type of condition, which was given as minus u comma x at x equal to 0 is h, that does not figure out explicitly. So, we would like to classify the boundary conditions in two types. One is the essential and the other is natural. So, these are from the perspective of the weak form. The essential boundary conditions are, these are explicitly satisfied in function spaces. So, you can see that u at x equal to 1 is G, this is explicitly stated, and likewise the w has to satisfy the homogeneous version of it. So, I will give you an example that u1 equal to G. On the other hand, the natural boundary condition is not explicitly satisfied. This is part of the statement of weak form. So, this is minus u comma x at 0 is h. You can see that this is kind of built into the statement of the weak form, and we will show that very shortly. Okay. All right. So, now the proof of part B of the axiom that if I satisfy the weak form, then I also should satisfy the strong form. So, I am now going to start with this statement. Okay. So, if u satisfies the weak form, that means the entire statement, then I already know that u belongs to the solution space, which means the boundary condition is given to me. Okay. So, that is a good starting point. It also satisfies this weak form, which I will analyze in a moment, but it should do that for all w's, not just for a single w or 2 or 3 w's. It should do this for all w's that belong to this set V, which means this statement has to be tested for infinite number of w's, okay? And that is why it is equivalent to the strong form. Okay. You will realize that the strong form, so let us again go back to the strong form. The strong form says u comma xx plus f is 0 on omega. So, this is 0 to 1 and this is my omega, infinite number of points. So, you can see this statement is valid here, it is valid at this point, at infinite number of points. So, if I had to write down, this would be u comma xx plus f equal to 0 on x1, on x2 and all the way to xn, and of course n tends to infinity. So, these are infinite number of equations. How can they be equivalent to one integral form? And the trick is that in fact these are also infinite number of equations because w's are infinite. So, my test function are infinite in number. So, if I write down my weak form, I would have this weak form should be satisfied for w1, it should be satisfied for w2, w3, wn, and n goes to infinity. So, that is the counterpart of the strong and the weak form. Okay, let us come back to the proof. So, let us say the solution u satisfies w. So, that means I am going to start with the statement 0 to 1 w comma x u comma x dx. This is 0 to 1 w comma x, sorry, w times f dx plus w0h. I am now going to integrate by parts the first term. Okay. So, I am going to generate two terms out of it, and let me write them down for you. So, the first one would be integral 0 to 1 w times u comma xx dx, that is the first term, and then there would be another term which is w u comma x 0 to 1, and this would be equal to 0 to 1 w f dx plus w0h. Now, this term here I can write as w1 times u comma x1 minus w0 u comma x0, and this has to be satisfied for all w's that belong to V, which really means that my w1 should be 0. So, therefore, this term goes to 0. Okay. So, I am going to get now the following equation. So, minus 0 to 1 w times u comma xx plus f dx plus, or rather minus, I would have from this term w0 and u comma x 0 minus h equal to 0. Okay. So, this is what has come out of the weak form after I integrated by parts. Now, if I want to show that the strong form is satisfied, I really need to show these two individually. So, I must show that I can get u comma x x plus f equal to 0 at all points in the domain, and I must also show that this u comma x at 0 is minus h. So, actually this should be a plus here, sorry. So, how do we do that? Now, remember this is satisfied for all w's. Okay. So, just like I wrote that u comma x x plus f is 0 and I could write it at all the points, now I can write that this statement holds for w1, w2, w3 and so on, and they all should hold concurrently for all w's. If I can take any one of those statements for any w and I can derive this or this independently, then actually the proof is complete. So, that is exactly what we will do. We will choose a certain w of x. So, let us do that. So, first I will choose, so define w of x as phi of x times u comma x x plus f, such that phi of x is always greater than 0. In fact, it is strictly greater than 0 on omega, and at the boundaries I would like it to be 0. So, it is phi 0 is equal to phi 1 is 0. So, one example could be that phi of x could be something like x times 1 minus x, and then you can see that if this is my x axis, this is my y axis, or I can show phi on this, then between 0 and 1 my phi looks something like this. So, it is greater than 0 at all points, but at x equal to 0 and 1 it is exactly 0. So, I am going to choose this very special w, and please notice that it does not violate the condition that it should come from V. Recall that w belongs to V. So, I must satisfy these conditions, that w should be square integrable and that w at x equal to 1 is 0. So, I have chosen some additional constraints on w which I am free to choose, because really this statement holds for all w's. Alright, so if I do that, let me call this as A. If I plug this special value of w in this equation A, so plug this special w in A, and then I will see that my w0 vanishes, okay, because of the way I have chosen the w, and I simply get the following. I would get integral 0 to 1 phi times u comma x x plus f whole square dx equal to 0. Now, notice phi is greater than 0 on omega, and u comma x x plus f whole square can only be greater than or equal to 0 because it is a square of a number, okay, and we know that we are dealing with real functions. So, u is a real function, its second derivative is also real, f is real, I add them, square them up. So, the answer has to be either 0 or greater than 0. So, now I require that this integral should be 0, whereas the integrand is greater than or equal to 0, but phi cannot be 0. So, this must imply that u comma x x plus f must be 0 on omega. Okay. So, I have been able to show that if I satisfy the weak form, then it definitely satisfies the differential equation. Now I can plug this back in A and show that minus u comma x 0 is h. So that completes the proof, and what I have done is that I started from the weak form and I have been able to show that I satisfy the strong form, which means these two conditions, the differential equation as well as the boundary condition. I hope this also shows you why this is called a natural boundary condition, because it kind of naturally arises from the weak form of the problem, as opposed to the essential boundary condition, which is explicitly stated in the function space. Good. So to summarize, what we have been able to show is that the strong form implies the weak form and the weak form implies the strong form, therefore they are equivalent. So it is these are two ways of stating the same thing. So if I want to solve a problem, I can either take the strong form or I can take the weak form, and they are equivalent, they are synonymous. Now it is just a matter of approximation. If I want to approximate the strong form, I would get methods like the finite difference methods, but if I start from the weak form, then of course I would get methods like the Galerkin method or the finite element method. So let us look at some notation to simplify the weak form. So you are already aware of the inner product. So we are going to say that W times F actually implies that we are talking about integral 0 to 1 W times F dx. So two functions separated by a comma in parentheses is the inner product. We are going to introduce another notation, which is the operator A acting on these two functions Wu, and this notation is that it is the product of their derivatives. Okay? It is just a notation. We could have come up with some other notation, and perhaps we will need to do that if we have a slightly different problem that needs to be solved. We will give you examples of those. So these are the two operators that we will use further as we move along, and now I want to talk about some of their properties. Okay. So you will notice that A of Wu is actually same as A of Uw. So this is the property which is called as the symmetry property, and the proof is very simple. I mean, this quantity is 0 to 1 W comma x u comma x dx, and this one is integral 0 to 1 u comma x W comma x dx. So they are certainly symmetric. Okay. The other is that they are bilinear. In fact, you will notice that this operator is also symmetric. So W comma F is same as F comma W. Okay. Okay, what does bilinear mean? That we have now a functional with two variables W and F, and this product that we have defined, the operator that we have defined, it is linear in both slots. So linear in both slots. So to give you an example, what we are saying is that A of C1 U1 plus C2 U2 W is actually same as C1 times A of U1 W plus C2 times A of U2 W. And likewise, if I use the second slot, so U comma D1 W1 plus D2 W2 is same as D1 times A of U comma W1 plus the constant D2 times A of U W2. I have assumed that C1, C2, D1 and D2, they are constants. And the proof is really simple. So suppose I want to prove this relationship here, all I have to do is the following. I take the integral 0 to 1. So this one is given as C1 U1 plus C2 U2 comma x times W comma x dx. And then I can break up this integral as C1 U1 comma x W comma x plus C2 U2 comma x W comma x dx. And if I open up this further, then I get C1 times A of U1 W plus C2 A of U2 W, which is really what we have written earlier. So that's the proof. Okay. So the property of these operators are that they are symmetric and they are bilinear. And in fact, these properties are extremely useful. As I mentioned to you that at the end of every method that solves ODEs or PDEs, you are going to get a system of equation Ax equal to b. And we will see that these properties of symmetry, they will lead to symmetric equation systems, which are really useful from a linear algebra point of view. Okay, so from this notation, we are going to simplify the statement for the weak form. So what we will do is the notations that we have prescribed, we are going to plug it in the weak form, and then the statement is going to look something like this, that minus A of U comma W plus W comma F plus W comma H on gamma is 0. This is the statement of the weak form, where I have already explained to you what is this operator. You already know what is the inner product. This one is a little bit new. So note that W comma H gamma is a boundary integral. In this case, the boundary is only 2 points, x equal to 0 and x equal to 1. So this is my x axis and I have 0 to 1. So this integral actually boils down to W 0 times h and W 1 times h. Okay. So this is a very compact notation for writing the weak form. So the statement of the weak form would be that given f, g and h, I am supposed to find a u from the solution space S such that this statement is satisfied for all w's that come from the space V. Okay. So very compact notation.